In the last video, we looked at quarks and leptons. In this video, we're going to look at naming convention, including the notation we use when writing down baryons and mesons. So here is some information about naming conventions we use. Protons and neutrons, we usually use a lowercase p and a lowercase n to indicate a proton and a neutron. Delta particles, they are very, very similar to protons and neutrons. They don't have any strangeness, nor do protons nor do neutrons. But a particle with a strangeness of -1 usually is indicated with a sigma. There are lambda particles, which also have a strangeness of -1, but they are more energetic versions of the sigma particle. Lambda particles contain an up, a down, and a strange quark, but we'll cover that later. There are Xi particles. They have strangeness of -2, and omega particles have a strangeness of -3. So there's a small list here of particle names that you can learn the strangeness for each of them. You can indicate antiparticles by drawing a bar over the top of the particle symbol. The antiparticles to these have the sign on the charge reversed. They also have the sign on the strangeness reversed. There are some names of mesons as well. So pi mesons and eta mesons don't have any strangeness at all. K mesons, that's kaons, they do have strangeness. Now, the first strange particles identified were kaons. And so originally, strangeness was tied to charge. A positive kaon was given a strangeness of +1. So that means positive kaons have positive strangeness, negative kaons have negative strangeness. But because the strangeness was tied to the charge, when a neutral kaon was discovered, it was given positive strangeness. It was strange because its half-life seemed a bit longer than we expected it to be, but it's got positive strangeness. And that means even though neutral kaons have no electric charge, you can get anti-neutral kaons. Charge sign isn't reversed because it's 0, but the strangeness sign is reversed. The convention for our notation is to use a symbol, like the ones I've just shown you, and then indicate the charge of the particle in the top right-hand corner. You will also see sometimes more exotic particles with C's in the subscript. A subscript C after the symbol indicates that there's a charm quark inside that particle. And a subscript B indicates there's a bottom quark inside that particle, and so on. Occasionally you'll also see a star up here, which indicates a more energetic version of that composite particle. More energetic version can be a bit difficult to get your head around. But if you can imagine, I can have an atom, maybe helium, which is neutral, and I can have the electrons in that helium excited to a higher energy level. So the helium atom is now in an excited state. It's more energetic. Well, you can do that with helium atoms without changing the composition of the helium atom. It still contains 2 protons, 2 neutrons, and 2 electrons. It's just one of the electrons is in a higher energy level. It turns out you can do exactly the same thing inside the nucleus. So you can have nuclei that are in higher energy levels, and metastable state of technetium is an example of that. But it goes deeper, and even within a composite particle, you could have quarks that are in a more energetic state that can decay into a lower energetic state without changing the composition of that composite particle, but still becoming less energetic. And also remember, in particle physics, energy is mass. So a more massive particle is more energetic. So you can use this notation to figure out the quark compositions. As I said here, it's a bit of a logic puzzle. Let's use this example here, sigma 0. We know sigma is a baryon, so therefore it has a baryon number of 1. We know if it's a baryon number of 1, it has 3 quarks. That's one of the definitions of a baryon. We know it's a sigma particle, so it has a strangeness of -1. That means one of the quarks has to be a strange quark. We know the charge on a strange quark is -1/3 elementary charge. But sigma 0 is neutral charge. We can see that because of the 0 in the top right-hand side. So that means the remaining 2 quarks has to have a charge that adds up to 1/3 to balance it out. Now, the only charge we've got to play with is a 2/3 charge or a -1/3 charge. That's the up quarks and the down quarks, respectively. We can't put anti-quarks into this because it's a baryon and it contains 3 quarks. So we need to have an up quark and a down quark. So when you add 2/3 to -1/3, you get 1/3, which is what we needed. So the sigma 0 baryon contains a strange quark, an up quark, and a down quark. We've used logic to figure that out. Now you can do that with all of the different symbols. Any of these, you could now work out the quark composition. We know, for example, 𝝌0. 𝝌0 has a strangeness of -2. That means it has two strange quarks. Now, two strange quarks together have a charge of -2/3. So we would have to have one 2/3 quark, which is an up quark, in order to make the charge 0. So this is one up quark and two strange quarks. You can do that for any of these composite particles. The ones on this right-hand side here and the ones down here, well, those are fundamental already. But all these from the K- up and all these on the left, they are composite particles that contain quarks and antiquarks. Remember, the symbol was determined by how strange it was, and the 0, minus, and plus was determined by the charge the particle has. And those particle properties directly relate to this very simple quark model. But I haven't yet explained what the W boson is doing, and I'll explain that in the next video.